Welcome to video 2, and this is network measurements with Pico. So in this video, Andy and I will describe a variety of measurement techniques that will enable you to evaluate the network under test and so minimize measurement errors. And on that note, how many times do we think we found a fault when it turns out to be a measurement error? And there are some errors you can make. The guided test will help and support, but even then, when you start making adjustments and what have you, you can get yourself lost. So little tip here, blame your measurement technique first if you think you've found something wrong, and prove and qualify your technique before you move on.
I mean, and this is a vital step, is one, refining your measurement process is vital, and practicing on vehicles that don't have faults,
yeah.
So you know that you're up to scratch with your measurement techniques and that you're doing the right thing in the right way. And secondly, if you do have a communication or a network error on a vehicle, you are going to have to measure it to find out what's wrong.
Yeah.
So getting good at this is bread and butter.
Yeah. And by measuring, we talked about non-intrusive, didn't we? The process of measuring is actually intrusive. So it's the next level of intrusion, simply connecting to a wire. So don't even think about breaking the connection, maybe backpinning. You are now joining the network with the tool, so you are intruding.
But it's the same with a scan tool, Steve. By putting the scan tool on the network, you're adding,
yes, you are,
if you like, a foreign object to the network.
Yes.
Albeit it's invited.
Yeah.
But it's nothing when we do this is truly non-intrusive.
Non-intrusive,
We're
yeah.
minimising the intrusion.
Yes, yeah. Levels of intrusion as necessary, yeah. So I have an animation here that, let me just run this animation, that takes us through communication networks. So here we'll see various topologies. So there's the terminology. So we have ring in there, we have what looks like engine management, lighting bus, ventilation, media, convenience, windows and such. Here we have the breakout box. So again, not always possible to get C.A.N data directly over diagnostic. It may be that you need to use our breakout box and link to the networks via the scan tool. So you're actually communicating over C.A.N with the diagnostic interface, the gateway, if you like, between the OBD and all those networks on the vehicle. Earlier stuff, quite possible you'll be straight on the network at the OBD connector, but one to be aware of. So this one, I wish this was my idea, but it wasn't, it was Andy's. So there you are.
Yeah, so I've been using this acronym when I teach people how to diagnose network faults. I come up with C.A.N. When the dominant protocol was CAN bus, I thought this was quite clever because I used the acronym C.A.N. And what we'll go through here is what that means. When you're faced with a network fault, you've got a 3-step process, which is establishing whether or not can messages be sent. Is the bus ready to send? Are messages being sent? Is data visible on the bus? And then node evaluation, your power, grounds and compatibility of that module, node or ECU on the network. And obviously it fits quite nicely with the CAN bus, having C.A.N as your network acronym to remind you how do you establish or have a process for diagnosing network faults. Using the C.A.N process that I've come up with is a fairly robust method. Steve, have you ever been having a go with my...
I've been using this last couple of weeks really, preparing these practicals that we're going to go through, and it works. Why wouldn't it? I mean, but just follow this. We talk about diagnosis and process, have a process, but this kind of just sits comfortable. Can messages be sent? Are they being sent? And then node evaluation. So we will prove this as we go through with a number of networks, but certainly just demonstrating these techniques, even in a controlled environment. Hopefully you'll see that it works and you can adopt this. So what am I measuring and why? using the acronym C.A.N, can messages be sent? Let's start with that. So a note here: for successful communication there must be a minimum of 2 ECUs and a data bus between them, because that defines what's required for communication. If you haven't got that, there will be no communication. There might be something that is babbling, sending data out, but nothing coming back, because there is nothing to receive, or nothing to hear, nothing to interpret. Before we actually get into C.A.N, I'll record any serial data communication faults. This is why we are here. This is why we're looking at the network. We are presented with a lot of codes, loss of communication with. Something that's helped me in the past is look for something that's common between ECUs. I call it pointing the finger. An ECU, multiple ECUs have lost communication with. So they're all sort of pointing to one computer, and also the computer that's being, shall we say, targeted will often be reporting similar communication errors. So record those. If there is note communication between the scan tool and the offending ECU is possible by requesting data. So it sounds counterintuitive, doesn't it, that other computers have lost communication. So why am I now communicating or trying to communicate with the ECU that won't communicate? It may be that there's another avenue. It may have redundancy or dual network. So there's a nice pointer that you can still talk to that computer, but you're going in almost on another avenue. In that case, power and ground must be okay. Yeah. Identify the network under test. This is something that kind of sounds obvious. Nothing's obvious, nothing is simple. It's only simple when you know. Is it a LIN bus? Is it a CAN bus? It might be a twisted pair, but there's 3 possible networks it could be as a twisted pair. So how do you know? Use technical data, training literature, and for those lucky enough to have product knowledge, that will carry you through there. Validate the physical wiring under test, single wire for LIN bus, twisted pair for CAN bus, etc. Wire colours as well. Using the PicoScope resistance lead, so remember we are at CAN messages be sent. Measure the network bus impedance, resistance to ground and continuity if necessary. And using PicoScope, an applicable test lead, and I've gone for what we call a ×10 test lead here. Why are we using a attenuated test lead to measure low voltage? Because typically we've always chose a high attenuation for high voltage measurements. Well, this is what we call a high impedance lead. I talked earlier about intruding onto the network simply by taking a measurement. By having this high impedance, we reduce the influence of our measurement tool on the network. So it's kind of a nice default go-to tool to measure voltages present on the bus, and are they relevant? What do I mean by are they relevant? Well, if we're just checking the voltage on a CAN bus wire and we see 12 volts, something's not right. You know? So just check voltage level. Is it applicable to the network under test? So resistance, impedance, voltage measurements using the acronym C.A.N, can measurements be sent. Graphing resistance over time reveals errors whilst wiggle testing. You mentioned this yesterday, Andy, wasn't it? That we always do that static measurement. Yes, we've got continuity, move on quick.
Yeah.
Without moving the wiring harness, without moving connections and that. And you will see deviation. There will be naturally, but is it excessive? Is it stepping over the mark? Is it more than just movement or flexing in cables? So from this process, we want to make sure the vehicle is totally dead before we're going to carry out a resistance measurement. And I thought this was fundamental step number 1, nothing to worry about here until...
If only it was that simple.
Yeah, you think disconnecting the battery, vehicle's at 0 volts, or is it? We'll do a test later on where we'll actually measure the differential, the potential difference between the positive and negative lead on the vehicle when we disconnect the battery. It certainly opened my eyes, especially on EV. So I think we'll cover that. Impedance measurement on the C.A.N, LIN and FlexRay. Is it short to ground as well? So not only does their network have a specified resistance, we want to make sure that while we're in there and the vehicle is dead, let's check for shorts to ground. Let's have a look at ground testing with milliohm meter. Remember, the vehicle is completely dead. We've got an opportunity now to measure the ground of the offending ECU, or what we believe to be the offender, with the milliohm meter. Let's truly send current through the ground and actually see if there is something other than something a bit more sinister than what we perhaps traditionally thought as continuity. See what the actual milliohm value is. And then check for voltages present on the bus. Why am I checking for voltages present on the bus when I've disconnected the battery and the system is, or the vehicle is at 0 volts? It comes down to aftermarket devices maybe, or devices that are self-powered. We know, I certainly had some very bad experiences of immobilizers that have chose to manipulate the C.A.N to prevent the vehicle from operating in the event of a theft, attempted theft. What a heartache that can be.
Yeah, trackers.
Yeah.
There are devices where people don't pay their bill for their car that stop them starting. All of those have a supplementary battery, which can, as we'll demonstrate, play havoc on the networks.
Yeah.
It's interesting you talk about the milliohm meter. There are other techniques you can use using the milliohm meter when you're looking at CAN bus, which we'll discuss if we don't actually demonstrate during the video.
Yeah.
Because it's interesting that extra visibility that you can have using the milliohm meter as opposed to the resistance leads gives you another avenue, another test you can do, especially for poor pins and things that are affected that you wouldn't spot in any other test method. Certainly, it's got me out of trouble once or twice already.
Yeah. And we will compare the accuracy between both. So we've got a resistance lead that we're graphing resistance over time, so we'll get the value from there, and then we'll actually drill down with the milliohm meter and see what the true value is. Interesting comment about trackers and such. One is subscription, so the other one is customer may have had a flat battery and then it's coming with an array of faults, and it's because whatever this device is that's manipulating the C.A.N has finally come online. It may have been redundant, now it's lost voltage, battery voltage, it's now powered back up, and then we have all this drama. So often there's a pattern sometimes to these things occurring. So remember that can messages be sent? We're looking at the integrity of the bus, the network. So we move on to the A, are messages being sent? So here we'll check bus voltages to reveal if the acquired values are relevant to the network under test. What do we expect to see? And now I've put a note in here, voltage measurements for speeds up to 500 kilobit per second are standard test lead, what we call a ×1 test lead. That means whatever the voltage is at the probe tip is the same at the scope. The lead has no influence on that, not really. That's okay, but when we start to get to high speed networks, we want to be using the high impedance lead, which is why I was defaulting to the high impedance, because if you don't know what you're measuring, then at least you'll be you won't be intruding, you won't be influencing the signal. You don't want to trip yourself up there. Things to look out for: these networks have specific voltages when they're asleep and when they're in standby mode, what we call recessive voltage levels. You know, what state is the bus in? Even, is it awake? Is it awake? Is it babbling? Is something on there that's babbling away? And then capture data messaging and apply measurements, including baud rates. So at this point, are messages being sent? It's not a bad idea really to maybe apply the decoder. We will come on to that, but here now we have powered up, we've got ignition on. Is there information out there being exchanged on the bus? Adding on to are messages being sent, with communication on the bus, voltage levels will rise and fall to form a pulse train at differing intervals. Sounds obvious, but again, you stopped me dead in my tracks. How do I know it's not PWM? How do I know what wire I'm on? Use the guided tests. Now the guided tests have a sort of default setting, so they'll get you a measurement on screen using the right probe with also an example waveform. So how do I know if what I'm connected to is the right wire and the right bus? Well, we have example waveforms in our guided tests, so you'll be able to keep the example on screen using the reference waveform feature. So we will do this as a practical. Then we can do a quick comparison. We'll know we're on the right wire. We'll know we have the right bus. Can we identify the network speed? Well, as we talked about, we'll measure the smallest bit and derive the baud rate. We will demonstrate ×1 and ×10 probe differences as well. Maybe not so much, we'll try both. We'll try C.A.N and we'll try FlexRay. We'll just see the influences your probe will have on your signal. We'll use what we call a math channel, and don't worry too much about that, because using our guided tests, these are already created for you. So you'll see if we're measuring a 2-wire twisted pair differential bus, you'll actually see the differential value. And we'll demonstrate some filtering of waveforms and also some of the dangers around filtering. And we have a terminology, catch it dirty. So capture raw data, as dirty as it may be, as noisy as it may be, and then from that we've got raw data that we can modify. Let's not modify whilst we're capturing. And then we move on to node. So with good voltage levels and signals on the bus, an ECU node can remain offline and fail to communicate if the power supply and grounds are not correct. So we did our ground test while the vehicle was actually powered down. It made perfect sense to use milliohm resistance lead. So power and ground testing, but here we've said that the ground may have been tested, but because we've got power, there is now an opportunity to load test it.
Yep.
So maybe place a load across the power and ground just to see that you can pull current. I think with what we've done previously, using the resistance lead and the milliohm, we should be happy that our ground is okay. But we want to pull something through the power. So let's see. Not all ECUs are the same physically. We seem to think of, and you mentioned this in your nodes, not all ECUs are a box with multi-plugs on them. There's one that we'll see, in fact it's there, the air conditioning pressure switch on one of the vehicles that we have is what we call a smart ECU, a smart sensor. It has computer on board and it has the ability to exchange data over a bus. Current clamp measurements. So here's something that's not new. We've had current clamps for many years. Applying them to networks reveals a lot of data, certainly in the exchange of data between computers and the direction as well. Might be able to prove if there is data leaving a computer that is allegedly offline. And check communication status. This is when we actually get down to proving that signals can be sent, they are being sent, power and ground is good. What have we missed? Online, is it online? Does it require coding? Does the computer need to be coded? Does it need initialization or configuration? These are all things that will be missed. And if they are, they will be flagged as being offline and no communication if those features aren't correct.
So it's important to say, Steve, because you obviously said about the power and ground testing, you don't have to apply this testing process in the order of C.A.N. You may start with N at the node, depending on how the fault is presented. It's just that we need to remember that for successful communication, in terms of our diagnosis, what we want to do is we want to check that can messages be sent? If they can, are they being sent? And then that really leaves at the end the node. As possibly the cause of the fault. But it could be that you know that node is offline because from other, your fault codes, etc., or other reasons, and that all you want to do is check at the node to begin with. Once you establish that, you can then move back to these can messages be sent, then are messages being sent.
Yes.
You don't have to go in this order. That's,
yes.
I think that's important to say, otherwise you could do a load of unnecessary testing here for a blown fuse.
But you've got it covered, all bases covered.
All bases will be covered.
I do like the fact that there is that acronym that will, you know, where do you start with this network? Yeah. And
I think, you know, from, you know, the number of vehicles we see that come in misdiagnosed with network faults, and on training courses, how little these procedures are understood. Having a process that around testing these things, I think, is really important.
Yeah, I do like it. Can messages be sent? Are messages being sent? And then finally the node itself. So we're now going to take a look at multiple bus faults and utilize several PicoScope measurement techniques to help and aid your diagnosis. So a couple of items here. We have single wire bus. We'll introduce shorts to positive and ground, introduce ground faults to the ECU, and note the effects on the messaging, what a ground fault will do. Voltage and current measurements on these buses and open circuits, and the same again really for dual wire buses. So we'll introduce an impedance fault, a loss of termination resistor. That's an interesting one, that doesn't always throw a fault.
No.
Take a termination resistor out, depends on the network, but certainly you'll be surprised what you can do with a differential bus before it actually flags a fault. And here we are talking about diagnosing multiple faults on vehicles. Yeah. It is incredibly fault tolerant.
Very, very fault tolerant. And certainly in the older days, some of the termination resistors were external. They weren't inside ECU, so you could easily lose one.
Yes.
Because, you know, damage or whatever, you know, or corrode off the network, and the network will be absolutely fine.
Still working fine, yeah. And you will see how we can change the voltage levels on the buses, and yet still we've got communication. Again, introducing ground faults, high resistances as well in both CAN high and CAN low, and the influence they have on the vehicle. So yeah, we'll move on to, let's have a look. We'll move on now into the workshop, and we'll run through those practical examples. Thank you for watching. Okay, so following the CAN principle, so can messages be sent? We're going to actually skip this bit about disconnecting the battery, because what is there other than disconnecting the battery? And that was until I checked to see whether there was any potential between the two leads. So disconnecting the battery positive and negative, just put the voltmeter across there, the scope. Sure enough, it isn't 0 volts. So let's just run through that and see what we have to do to ensure this vehicle is totally at 0 volts. So we'll disconnect the battery. So at this point, we would expect that to be 0 volts. But if we just measure the difference between these two leads, and then let's have a look at the scope, we'll see there that we're not at 0 volts. Now, that stopped me dead in my tracks, because we talk about measuring continuity reference to ground. Now, I'm sure that will dissipate very quickly, but clearly not. 871 millivolts, where is that coming from?
It's a good point, Steve, and you know, obviously if you don't stop and think about it, you'd never consider what that is, and you would just assume, and we all know what assume means, that, that it is 0 volts.
Yeah.
But obviously the leads are still connected to the vehicle.
Yes.
Although they're not connected to the battery, and the components within the vehicle contain capacitors.
Yes.
Which are now storing electricity, which is slowly dissipating.
Yeah.
But how could we speed up the process and get it down to 0 volts?
Yeah, well, what we'll do, we'll short the two together.
This voltage, that residual voltage that we're measuring there, it could be enough to retain memory in certain components, and there are many components within the car that have memory.
Yeah.
And we need to, and often this is a technique that technicians use anyway to get rid of.
Sometimes to get out of jail.
Yeah, absolutely. Yeah. So we're using it to make sure we're at 0 volts.
Absolutely. Now we'll run it on this car. It's very, very quick to dissipate all this, but we'll come to another test a bit later on where it's not so straightforward. So this is just a case of joining the 2 leads together. Make sure that we put this through a fuse as well, just in case there's something residual there beyond capacitive discharge. So let's go on here. And let's pull that right down to 0 volts. In fact, you could see earlier on how that was starting to dissipate anyway, but we'll leave that on just for a few seconds. We can be assured now that this vehicle is truly at 0 volts and shut down, so we can proceed with the next test.
And it's important, once we have shut it down, then you remove the jumper.
Yeah.
You remove the jumper before doing your testing.
Yeah, good point. We'll remove the jumper now. Let's just see that, we'll make sure that that does not start to creep back up.
And then make sure it doesn't go back up.
Yeah. Which it is. I don't know if you can see that. It's just slowly but surely.
Yeah.
Yeah. Okay, we'll leave that on a bit longer because somehow there is something still. Yeah, we saw it just drop there. It is discharging slightly. So we'll leave this on and then we'll move on. We mentioned earlier in the video how we'd spotted something more so on electric vehicle, and that's what we have here. We have our e-Golf doing the exact same thing, disconnecting the battery and looking at residual voltage. It was quite surprising what we found. So you see here that the system is shut down. We're happy that it is. I've left the signal ruler in at 12.42 volts. We're measuring across the battery there. There's an indication that DC-DC is not working, so it's not charging, and it shouldn't do anyway because it is shut down. But let's move on. So we'll disconnect the battery. So we'll take off the positive terminal, note the voltage there, and take off the negative terminal and just pack them there as well. So now we are not connected in any way to battery voltage. Just look at the decay there, how long that's taking. Now that did surprise me, just how much residual and capacitance there is left in the vehicle. It takes on a mind of its own there, doesn't it? So we can short that out. So again, cross negative, remember, via a fused lead, and that shorts it straight to ground, as you'd expect, or certainly 0 potential between leads. Disconnect, and just note what happens now. That capacitance is still there. There is still residual in this vehicle. So we found with electric vehicles that this really needs to be, the jumper wire needs to be on for considerable time, just to ensure that that voltage does not creep back up again, and just repeat the test. So when you take the jumper lead off, it should remain at 0 volt. Okay, so can messages be sent? The first one was, of course, we've made sure this vehicle is at 0 volts and fully discharged. We wanted to check before we go down the impedance route, actually for voltage on the CAN bus, which you ask yourself, well, the vehicle's dead, so why are we doing that? In my experience, I've had a couple of issues, and I think you mentioned, was it tracker?
Trackers, yeah.
Anything self-powered on the vehicle that may be connected to CAN has a potential to leave voltage on the CAN, especially when we've got the vehicle disconnected. So we'll check for voltage here. We can see that they are at 0 volts on the CAN network. We've measured across both sides. Ultimately now we'll move on with an impedance check. So initially we'll use the resistance lead. We're looking for that magic 60 ohms. So let's connect. The scope's going to automatically recognise the resistance leads connected. What's important here is that we use the right range. So we want minus 50 to 200. What is it you said? Expect, what was it?
Expect what you inspect.
Expect what you inspect. There you are. So we're looking for 60 ohms. We know we want that kind of range. And also just join the leads together so we can actually see that we are at a true 0. So we are there. So we join across CAN high, CAN low. And all things being equal, that should be 60 ohms approximately. So we'll pause the scope and we'll add a measurement. So measurements, and channel A, we want the mean value. So there lies a 57 ohms. Is that a fault?
Good, bad or indifferent?
Good, bad or indifferent, yeah.
Like to ask people.
We've got to allow for tolerances, we've got to. So I think at 57 I'm happy to move forward.
But you know, it's a good chance to sort of pose the question, what can affect the resistance of a conductor?
Well, a combination, isn't it? We've got connections first of all.
Absolutely.
Connections, cables, termination. I don't know what the specs are in terms of absolute
so tolerances?
Tolerances, yeah.
Okay, but obviously it depends on one big variable, temperature.
Temperature, of course.
Length of the conductor,
yeah.
and cross-sectional area.
Yeah.
Yeah. All of those things will affect the resistance of a conductor. So
yeah.
beside all of the other influences such as connections.
Yeah. But in your experience, would you go 57, I'll accept that?
A general rule of thumb, 10%.
Yeah.
So we're going to plus or minus 6 ohms at this stage, and
we'll move on. So an additional check that we can do at this point, let's just check C.A.N reference to ground. We know the impedance is good. We'll just simply leave one of the leads on and connect to chassis ground. And as you'd expect, an open circuit. Just to play devil's advocate though, let's increase the resistance, and all of a sudden, let me just pause that. That's interesting, 279.2 ohms. So this is C.A.N high, reference to ground.
Which is interesting.
Suggests,
because we'd expect that to be infinity or open circuit. But we actually have a ground path on C.A.N high. Will we have a ground path on C.A.N low?
On C.A.N low. Carry on running the scope. So we move the lead across to C.A.N low. So now we're C.A.N low reference to ground. And that is, well, if we pause that, still the same, 279. So here's where my mind is right now, that I was expecting infinite resistance, and we haven't got that.
Which means,
thinking that through,
via one of the many controllers connected to a C.A.N network, we have somehow a path, albeit a tortuous one, to ground.
Yeah. Okay, so on that note, C.A.N high, C.A.N low to the transceiver microcontroller, and then through there somehow
it's finding a ground path.
Finding the ground.
But what we've established, there isn't a short to ground.
Correct. Otherwise that would have been zero. Okay. Keep that in mind. We'll move on to the next step. Okay, so this is an opportunity also while the vehicle is shut down to have a look at the grounding on the ECU. So let's just see how this ABS is referenced to ground, whether we've got a resistance there. We know that this is part of what would be a node check, but again, let's just take advantage of where we are. So Ben, if you want to come in here, we're going to just actually disconnect the ABS ECU. And we'll check for ground on this computer. There's a couple of ways we can do this. So the first way is we will use our breakout cable, and then we'll use the resistance lead. So we're going to come in, obviously reference to ground, so we're going to connect here. We want to be on the lowest possible range on PicoScope. We need to take this down because we were previously on a higher range when we discovered that sort of link to ground through the transceiver. So there we have 653 milliohm on that cable. We'll just move across to the other one because there are two. What was that? Yeah, 506. So half an ohm resistance. Could we test that more thoroughly? You suggested load, Andy.
Yeah, I mean, typically we would test grounds under load. But because the vehicle is dead and we've confirmed that, if you are in a position where you can't power an ECU because it will not power up, how then could you check that ground? If you suspect an ECU isn't drawing any current, you can't prove the ground using a traditional volt drop because volt drop requires the circuit to be loaded. If you can't load the circuit, then this is the next best step.
Yeah.
But personally, I feel this is a little bit, I'm going to say the word flaky, because we got 506 millio. Is that good or bad? We don't really know. So we need something a little bit more conclusive and something a little bit more accurate.
So at this point then, more accurate could be the milliohm meter. I think we will run that, we'll do that test.
Absolutely, yeah.
When we actually get down to node as we follow this flow, we could then truly load it.
We can truly load. There are other ways of loading it, and we can show that test later.
Yeah.
But
so
while we're here,
why not? Yeah. So we'll move over to milliohm meter and see how they compare. So following on from the PicoScope resistance lead check, let's have a further look at the resistance through using the milliohm meter. So open up the PicoScope software for milliohm and motor tester. This is where we're going to use a different measurement technique. So Andy, you talked about load.
Yeah.
Now with the milliohm meter, we are going to apply current through the measurement. So what's going to happen here is what we call a 4-wire measurement using the Kelvin method. We're actually going to measure with high accuracy by passing a current through the ground cable at the ABS ECU, reference to ground, actually see what the true value is, and then whilst we're in that position start moving the wiring harness and see what happens there. So USB connection to the milliohm meter. We're going to switch it to milliohm meter mode rather than using the motor tester. This will be just testing 2 cables. You'll see here we got 2 probes. We do need to add to our clips a male connector so that we can actually open the jaws of the Kelvin clip so that they'll actually grip the clip. So Ben, if you come in, you'll be able to see this a bit closer. What I mean by that is, here's our breakout lead that goes into the ABS ECU earth cable. I'm going to push this into here. That's going to give us a great measurement point so that we can put the Kelvin clip onto there. So you see how the jaws are held apart. Same again here. In fact, if we just give that a bit of a scratch, because we want to make sure that we have got a true earth. Bring that into here. Notice also that we've got temperature. Like you said earlier, Andy, temperature does affect resistance. And we'll actually see what we've got there, and right now it's saying 98 milliamp. It's saying it's out of bounds. That's because we're not on auto. So we'll set that to auto, that's better. So the scope said 500 milliamps. Yeah, we were happy with that. Milliohm meter is giving us a true value now. We're passing current through that cable. Not a lot of current, nevertheless, we're passing current through. It's a 4-wire accurate measurement. If I start moving the wiring harness now.
And that's the beauty of graphing this.
Yes.
You can start to see, and obviously it can look a bit dramatic, but you've got to always check your range on the graphing. Yeah,
so what that was there, that was actually when I moved that there, that almost looks like what would be a problem connection. It's actually because I'm pulling the connector in and out of the ABS actuator cable connector. So moving the wiring harness here, let's tug through here. I think we're fairly stable at that. I'll move it across now to the other side. So we've got 2 earth cables on the ABS ECU. And the opposite one again. Well, as you'd expect, they're both taking the same route in the harness and terminating at the same point. So on that, I think I'm happy to move forward that we have sufficient ground at this stage, yeah, with the load that we can apply.
Yeah.
Yeah, we can move on to the next step. Right, so can messages be sent? We're happy with that. So impedance, well, when we say impedance, we're still a bit curious about that, what we thought was a short to ground, but let's see what effect that had on the bus. So can messages be sent? What we're going to do is we're going to apply the guided test here. Ben, if you just want to come and see how we're connected, we've just used the ×1 test leads to connect to CAN high and CAN low, and they're both referenced to ground. So we would go to the guided test menu, communication, and this is going to be CAN bus. And at this stage, we're just interested in messaging, voltages basically.
Yeah, all we're trying to establish is are messages being sent.
Yeah. So we'll go for guide and settings file. This is what you would be starting with. You mentioned a great term, just-in-time learning. So if you've not measured CAN before,
great resource.
Here we go. Yeah. So we are connected already. What we are not connected like is this fashion. So just a quick mention here that you won't always get C.A.N at the OBD pins 6 and 14. On this vehicle, and it surprised us in that this is an early one, but it still goes through a diagnostic gateway ECU. So we want to actually get on the network. So we have gone straight to the wires at the ABS ECU. That's what to expect. That's sort of an example waveform. There's a lot of information here, further guidance. Definitely when you're training, even if you're not, an experienced technician.
Absolutely, yeah.
Just that just-in-time training, the guided tests have always got the further guidance in there. We'll minimise that. There's the example waveform. We haven't got to worry about settings, that's already done for us.
But wouldn't it be nice if you could have an example waveform on the screen at the same time as you test it?
Right, so this is a reference waveform. Because
right.
what will happen now is if I press the start button, this waveform will disappear and we'll have a waveform replace it, hopefully, if there is movement on the bus or activity on the bus. But we'll go for reference waveforms and we'll simply duplicate channels A and channel B. So you'll see there that we've now got lying underneath. If I just click and drag that, you see we've got a almost a ghost, if you want to call it that, of the example waveform.
So it's a shadow, effectively.
Yeah, great explanation. So press start, and there we have it. In fact, it gets a little confusing at the moment because of the speed of the network, but let's pause that. And let's get some, in fact, the quickest way to separate all your waveforms is to go auto arrange, which admittedly that seems to have compressed everything, but let's go back again. Views, we'll go reset. We'll pull them apart manually, so all I have to do is click on the scale here. We'll take away, bring down our references, which are the sort of lighter colours, lighter blue. So there's our reference waveform. And this is the waveform that we've actually captured on the bus. So let's just zoom in on the whole thing. So first impressions, Andy?
Looks pretty similar.
Yeah, let me put my glasses on. So we're interested in residual voltage. So C.A.N high at 2.5, C.A.N low also, hopefully recessive, 2.5. C.A.N low switching down to 1.5, C.A.N high switching up to approximately 3.5. So we see that here in the ruler legend. I think all in all, can messages be sent? Are messages being sent? Yeah, at this stage. Yeah.
You'd say there's messages on the bus.
Yeah. So with that, we will move on. All right, at this point, this is a golden opportunity to save what we consider to be a good example. So let's save this file. So we click the save. Now then, it's important if we're going to save this to keep all the details about this vehicle with the file. Luckily, I've already created in the past saved data for this. If I click on Audi A2, it has pre-populated everything about this vehicle. The only thing that's missing here is the channel labels. So if I type in or start typing in C.A.N, we'll see there it already pre-populates with C.A.N high, C.A.N low. You'll notice also we are going to say this is good. We know this is good. We are going to save the file and upload. Upload is actually, we're going to put it on the waveform library. So this waveform that you see here will go up to the cloud, and then anybody with a PicoScope can search for this vehicle, powertrain, C.A.N high and low, and download this example. So we click save and upload. Need to log into the waveform library. So use your username and password for the Pico forum, auto forum that is. You need an internet connection and you need PicoScope connected. And there it is. So at the moment it is waiting to be uploaded. The fact that it's in there, that will be uploaded accordingly. That will remain in my waveform section, but ultimately that will be there for everybody to be searched. It'll also generate a waveform ID, so we can include the ID later on in the presentation, so you'll be able to click on the ID and go straight to that waveform. So with that then, let's have a look at are we on the right network? Because we said we've got a twisted pair. We happen to know we're on powertrain CAN. We're right at the ABS. But let's say you were presented with a group of twisted pairs. We've got a CAN fault. How do we know we're on the right network? How do we know we've got the right speed and right baud rate? So for that, we would measure the smallest bit of the packet that we've got on screen. So we know that the lower waveforms are our example waveforms. I'm just going to zoom in here and use the rulers, time rulers. Let's try and be as accurate as we possibly can. We would expect 2 microseconds. That's what we'd be looking for if this was 500 kilobit per second CAN. And let's have a look at this. We have got just over 2 microseconds, 2.006, which equates to a baud rate of 498.5 kilohertz, 500 kilobit per second CAN. Now then.
And you were able to identify the smallest bit?
Yes.
Because it's the acknowledge field?
Yes.
And how did you notice it was the acknowledge field from the waveform?
Great question. Let me just move these rulers out the way. Now the acknowledge bit is right at the end of the packet with CAN, and generally if all ECUs have acknowledged, the amplitude will be greater than the rest of the packet. So on that, if we bring these 2 rulers down, if we would say that that would be what we class as our signal top, yeah, sort of a bass top if we exclude the ringing and the overshoot, we've actually got an increase in amplitude of 435 millivolt. So don't think by any means that's a fault. That's actually what we're looking for. We want to see the acknowledge bit at the end of the packet greater, because all ECUs on the network have acknowledged receipt of that message and have sent out that signal, which ultimately increases the amplitude. So.
And that's purely because they're on parallel circuit?
Yes, yeah.
And they've all broadcast at the same time?
Now, I think on this vehicle, 6 ECUs.
It'll be something in the order of that, yeah.
Yeah, it's relatively small, but nevertheless, there's the effect of 6 ECUs all acknowledging receipt of this message. Okay, so we're happy that the signals are correct, we've got the right baud rate, messages are being sent. We want to capture the recessive state. This is where we are sort of ignition off and power down. So CAN will go through a kind of a shutdown procedure. In my experience, it varies. I mean,
absolutely, from car to car. It can be up to 20 minutes or more.
So it's a long time to wait. What I'd like to do is sort of capture the point where we ignition off and we go down to the recessive state, so where messaging stops, and then ultimately capture where it goes to sleep, because that's what's really important. We want to make sure that it does truly go to sleep. So we're going to need to modify the settings to do that. What we'll do is we'll plot this on something like 200 millisecond divisions, which is a neat frame, a neat speed where you can actually see the waveform being drawn in real time. We call that streaming mode. You'll see that the reference waveforms, they've disappeared. They are actually on screen, but because we've changed the time frame, they've gone from what were captured at 50 microsecond divisions, I think it was, now down to 200. So we take that away. This is a great opportunity to see in real time now where we actually turn the ignition off and capture the point where we go to recessive, and then ultimately to sleep. Whether we'll capture it in one buffer, I'm not sure. Let's see what happens. So Andy, if you can turn the ignition off. Okay, so we'll go back through the buffer, have a look what we've captured here. So you see the point where Andy turned the ignition off, we got messaging up to this point here. Let's just pull a ruler down. Really, there is, looking at this here, we actually go from 2.5 volts immediately down to, let's say, just under 1 volt. Then we come down again further still, down to 0.9. Okay. We'll run PicoScope again. I'll take away that ruler. We'll take away the trigger. The trigger is no real help at this point. And, well, how long is this going to take now for this to actually drop down to 0 volts? That's really what we want to see, because anything that's holding the bus level at that voltage has a potential to give us parasitic drain. So
So
let's
put a really long.
Yeah, well, if we're going to go 20 minutes, really we want to be sort of up around 200 second divisions.
Yeah, something like that.
Yeah, and okay, we'll leave the ruler in place because we'll be able to see any deviation. You can see the blue waveform just appearing now behind the signal ruler for channel A, channel B. Yeah, we'll leave that running and see if we can capture the actual point of this network going to sleep. Okay, so we have come now down from the standby voltage to what we believe to be the sleep, which is kind of, again, another revelation here, is we were expecting 0 volts. It may be if we left this capture running for longer that we could maybe see it drop, but what I'll do here is, well, first of all, we'll have a look where we went from, where we left off at 900 millivolts. The time span was 9 minutes 17, so we did throw out sort of 10 minutes, 20 minutes out there, but that could vary depending on environmental conditions as well and vehicle operating conditions. We seem to have been at this level now. Let's pull this ruler down. We are at now 217 millivolts. I'm going to use the reset feature. So if we go to the views and reset, we can see there that both waveforms are sitting on top of one another, which means there's no differential. The fact that there's no differential, no current flow. Wouldn't it be great if we could wait all day long? Maybe as we carry on through these tests that we're going to do, whether we'll see that drop to 0. I think that's a valid waveform to send up to the waveform library because it could help someone somewhere. So again, how will we do that? Let's just click on save. We've already populated it here, Audi A2. We must fill in the channel labels. So CAN bus high, CAN bus low. And let's put a note in because hopefully this will help a technician. We'll put them down as good. We know at this point with this vehicle at this stage there is no fault, and save and upload. So there we are, that's gone up to the cloud. And there we have it, and we'll then move on with the CAN process. We're now going to look a little bit deeper at the CAN network. So we're happy with the physical layer, the actual structure of the signal. Let's have a look at the messages in more detail. So we'll go for now the decoder, which introduces something called the math channel. Now that gives us the differential between CAN high and CAN low. We talked about differential twin wire buses in the video. We'll actually see that in action and we'll see how we get noise cancellation. Let's download the guided test for for serial decoder. So guided tests, communication networks, CAN bus, serial decoding, guide and settings file. So again, explanation here. We did mention earlier about we can't always get powertrain CAN at the diagnostic connector. We'll see here how the example waveform has changed now. We've got a lot more data on screen. We're actually streaming, so we're at 200 millisecond divisions. You'll see the waveform being drawn slowly from left to right in real time. And beneath, what we have is the decode table. So we'll start to see things like CAN IDs and the bytes associated with the data within that packet. So we'll minimize here. There's our example waveform. I'm going to start PicoScope. Okay, so we are at what we believe to be our sleep. Yeah. At this point now, we'll turn ignition on. That will wake up the network and we'll capture data bytes. There we go. We haven't got to worry about stopping the decoder at that point. We'll actually let it run for a couple more buffers and have a look what we've got. So at this point we'll pause here And let's go back to the wake up, because there is diagnostic information in the wake up. There it is. Various stages as well. So we go from our rest or sleep. Oh, I think it was around about 880 millivolts. Here we come up, first stage was 1.46. Really, we're aiming to be at the, excuse me, the recessive voltage, which is 2.5 volts, and now we see C.A.N messaging. So what I would really like to show now is the math channel. Let's zoom in. We'll just go on this very first packet here. There you have C.A.N high and C.A.N low. I'm just going to drag this up so it comes into view. There we have 0, 2 volts. Remember we talked about the differential. So this is C.A.N high minus C.A.N low, 3.5 minus 1.5. That would give us 2 volts. 2.5 minus 2.5 gives us 0. So we see here the differential. And the decoder is actually giving us the identification here. Then we've got our data bytes, our CRC, and then end of message. So right now what we're drilling down to is the coding or the decoding of this information that's passing around the network. How can we see within the decode table whether we have errors or not? So let's just have a look in more detail. If we scroll down, we'll see here that we have a buffer that is highlighted red. So if we double click on that, we can see that we have an error here in this packet. Now, for what reason? At this stage, I'm not clear. It looks like it never actually completed, never got to end of frame. And it looks like we actually started broadcasting, or another message came on immediately at the end. Whether that is a fault, let's see if that's repeated as we scroll down. Yes, there's more errors here. Yeah, so there's quite a few errors as we go through. Now we know that we have been disconnecting and reconnecting various ECUs on this vehicle. What would we expect to see? Well, we could use an example from the waveform library. So we have got the waveform library open. Now we could search for a similar example. So we want to search for an Audi. Sorry, not a vehicle type. We wanted make would be Audi, of which we have 452 at the moment. We want an A2. And perhaps the quickest way would be to search by channel label, and we're looking for C.A.N. C.A.N high, there is 1. Let's click search and let's see if the criteria is met. Okay, so this is a ICE, of course, A2. It's same engine code, same model code, generation, sorry. Yeah, it's got C.A.N high, C.A.N low. It's also got a current clamp on here as well. And it was uploaded by me. Well, what are the chances of that? All right, let's download the waveform. So as the waveform comes down, we'll be able to see, or at least decode on this information and see if on this example we had errors. Okay, so for now we'll take away or just hide channel C. We've got very similar sort of structure to our C.A.N. We're okay in terms of the actual physical structure. Let's apply a decoder. So serial decoding. No, sorry, let me apply a math channel because we want to decode on the math channel first. So there's an A minus B, that's better. So we've applied the math channel. And now let's apply a decoder to the math channel. So serial decoding. We'll go for C.A.N. We'll go for C.A.N on A minus B. Now a little tip here in terms of your settings. The software has chosen 1.5 volts as the crossing point. We'll try go midway through the signal, so we'll go for something like 1 volt. And then with hysteresis, you want to go with sort of half again. So 1 volt takes you through 0, 2 volts, straight through the middle. If we go for another half a volt there for hysteresis, that's allowing for noise on the waveform. We're going to call it C.A.N. This is the correct baud rate. We know that because we measured it previously. Click next. We only want to decode this current buffer and click finish. So we're just waiting for the data to compile there, and we just drag the decode table up. Okay, so in this example, as we scroll down, we're not seeing any errors at all. Okay, so maybe the errors are valid on our vehicle. In this environment, we know most of those errors have been placed by us working on this vehicle, but this would be a method that you could use if you have got multiple errors. A quick way to look for an error, rather than scrolling through and looking for a red table entry, would be to go for search by valid. And there is one there. So at the moment, an invalid message highlighted in red. If we double click on that, well, the reason that is invalid is it's right at the end of the buffer. So in fact, we've actually run out of buffer before the message could complete. So we can ignore that. So the takeaway with this, that is an example waveform from the waveform library. We've been able to download that, and we could clearly see that on our example waveform, there were no errors in the decode table.
So not only are messages being sent, they're being sent successfully.
Successfully, yeah, and acknowledged accordingly.
Which is just the next level up.
Yeah. So the decoder, we'll use the decoder more so with diagnosis, but there's a quick introduction of going that next level beyond just looking at message structure, looking at far more data in far more detail. Okay, so the final test, let's just run through where we are with can messages be sent? Well, they prove the integrity of the network, that was good. Are messages being sent? Yes, they are. Yes, we did have a few errors. I know that we may well have implanted those ourselves. And then finally, we come to node, and this is power and ground. So we'll reset the configuration for PicoScope, because at the moment we have still got the guided test up. We'll go to reset configuration. Now, the way I've got PicoScope configured here, it will just go back to measuring plus or minus 20 volts at 200 millisecond divisions. This is just so that we can simply measure the power supply to the ABS ECU, the permanent feed that is, and then the ignition as well, and reference to ground. That in itself is not enough.
No, but there may be, people who believe testing for power and ground at the ECU is simply that, connecting a meter or a scope to the pins and seeing if you have a ground and a live there. But we discussed earlier on when we were doing the milliamp testing, yeah, that the best way to test these things is loaded.
To load it up, yeah.
Load the circuit. Now you may not be able to load the ECU if you suspect there's something wrong there, so you need to apply an external load, and that's what we'll go through now.
Yeah. So we'll do, Ben, if you want to just come in and have a look here. We're using the breakout leads on the ABS connector. Always have a look at the drag, we call pin drag test, to make sure that these pins haven't opened out. These are the correct sizes for these terminals. So here we have our permanent feed. That was the ECU earth, which we have checked with the milliohm meter. Nevertheless, we'll load it. This one is ignition. So if we just went to power supply and reference to ground, we see on the scope there that we're at 12 volts, and we think, well, okay, we could move on. Same again, we could do the same with both, but we'll just run with this test. Andy, could you just turn the ignition on so we can see that we have the ignition supply?
Certainly. That's
there we are.
Ignition on. So
ignition on. We leave ignition on at that point. So is that enough? Let's actually apply external load. So now, to measure voltage drop, we want to measure, let's take this out. So this will go into here. This will go onto the ground. There we are. Now we're going to change the range on the scope. Let's get that right the way down. Let's pause that. Let's apply a filter. Let's apply much more filtering than that. See if we can find out just how much noise, how much voltage drop we had on there. We have a 21 watt bulb with 70 millivolts volt drop on there. At this point, we're certainly happy that we have loaded the power supply and the ground, and we're happy that from a supply point of view, we're confident that there is no issues there. All right, so capture the voltage drop on the supply. So we're just looking at voltage at the moment when we apply load. So if we just let the PicoScope run, and at that point there, and then remove and pause PicoScope. Now if we go back through the buffer, we see the precise point where we applied load to the circuit. If I just pull this down and change the scaling slightly. In fact, maybe if we use the zoom, we can zoom in on this point here. That's where the load came off. Let's go back one more buffer. So there's a point where the load went from off. There we are. So this was the supply. Main supply was at 13.65. Then we applied the load to the circuit and we were at 13.48. So a voltage drop of 174 millivolts on the supply side, and as we saw on the ground side, was it millivolts again? So we are at that point confident that power supply and ground to this ECU is okay. Now we'll look at serial data. If we still have no communication, that's where we need to just come in with the serial data and find out, is it configured correctly, does it need initializing coding, etc. Okay, so we're going to summarize here exactly what we've just covered in those previous videos, and that is, let's say for example we've got a DTC communication error on a network, not necessarily CAN. Let's follow this CAN process. CAN messages be sent. That's where we were looking at things like the impedance of the network, the short to ground. What was interesting on the short to ground we had here, it turned out not to be relevant. This was what we thought was a short. I can't remember what it was. Was it over 260 odd? Oh, 270 ohms. Yeah. So that was proven. That must have been leakage through transceivers. Yeah. This has caught, not to say caught us out, but it was a bit of a revelation. The fact that we got voltage, a differential across the two terminals of the batteries leads when they were taken off the battery. I like this, checking node ground using milliohm. That was a way of loading the circuit when the vehicle was dead. Next was ARM messages being sent. So ignition on, check bus activity. We went through the sleep, the standby, and captured the wake. Used two guided tests, if you remember. The first one was the physical layer, just looking at the structure of the signal. We went a bit deeper then with the decoder. Capture messages, check the structure. Apply the math channel. We talked about the differential. Yeah, only relevant really on a twin wire bus.
Absolutely.
Yeah, if this had been Lin, then no point.
But at that point, we're not only sure that messages are being sent, we know they're being sent successfully. Successfully,
of course, because of the acknowledged signal.
Because of the decoder.
Yeah, and the decoder. Yeah, interesting. We could use the waveform library to pull down an example there. I mean, it's a little bit of a controlled environment here, isn't it? Real world. I would hope there was one up there. Possibly. Remember, it's not unusual to have the occasional error you'll see on other networks. That's tolerated. If a message wasn't acknowledged within its allowance, it will try again.
Yeah.
Next one's acknowledged. No need for a fault code.
No.
Not at that point. Apply decoder, and then the next is the node, isn't it? This is just power and ground because we had a communication error. Remember to load the circuit, that's the key. Yeah. Power, ground, voltage drop. Check communication status. This is the device online. Can it physically be seen with the scan tool? And check the software level coding. It might be that all of this is okay, it just simply is not initialized, configured, or configuration for the vehicle. I'm trying to think of the other terminology. Either way, the fact...
The only thing to add to the node test here, you may have a module that's online, is communicating without error. However, a function may not work, and then you would do something called a function check, which is basically making sure that function works via the various different ways you can make it work. That's all part of the node check. But if you've done all of that above that, you're probably left with software as or configuration or coding as possibly the error.
Or worst case scenario,
Yeah,
the ECU itself.
it could be.
Yeah,
it could
always reluctant to just go for ECU because
we've-
there's so
we've-
much to do.
You have to rule everything else out, and that is quite a comprehensive way of checking any network. You just need to know, you do your just-in-time learning, make sure you know what network you're working on, expect what you inspect, and then do the testing that's applicable to that particular network, following the C.A.N testing procedure, which is, can messages be sent? Are messages being sent? Are they being sent successfully? And don't forget to check the node.